we need to have a vacuum. We need to have a source of electrons. What is our source of electrons?
Cathode.
Yes. More specifically, if anybody remembers from yesterday. Well, that's
Electron cloud.
you are nailing it. Yeah, but like there's one more word.
Yeah.
The little piece, the piece that does it.
The filament.
Yeah, girl. Filament. Thank you. Yeah, I mean all of those were right. Yes, that was all part of the process. The name of the process, what it is. So yeah, but the actual piece where they're coming from is the filament. Then we have the target, which is part of the anode, and then we have to have that super high voltage. Where does that come from?
Step up transformer.
Oh gosh, just warm and fuzzy answering those questions.
Love it.
Okay. The cathode and anode are encased in an envelope. And so we're going to talk about the envelope in a minute. And it can be glass, it can be metal, but we talk about that in a minute. And then that envelope is again encased in a protective housing. So the protective housing is actually what you can see back there. Behind the handles and where the numbers are, that big old, I don't know, lumpy thing, that's the protective housing. So you got the anode, like if I'm looking at it like this, the anode's on the left, the cathode's on the right. A lot of times they are labeled on there too. I can't remember if that one is. I look every year and I cannot remember.
I know the portable is labeled. I don't know
Yeah,
if these ones
and I
are.
think the rooms
I think they
back there are.
I didn't think the CR room was labeled. The DR room might be.
One of them, I think maybe the DR one is. 2008. Wow.
It's almost as old as my car.
Alright. Maybe I won't look next year.
Yeah, I think it's the DR portable.
Anywho, sometimes you can label them. Anyway, you know which side they're on. So, but this is one picture. If you Google X-ray tube, you're going to get this picture. You're going to get a picture from all the other dang textbooks that I've used, and some that I haven't used. But it's good to look at all the different ones, right? Because yesterday I said I might be throwing pictures at you that are not from this book. So you still have to understand where things are located, what they might look like differently in the pictures, okay? So I do have a few different ones tossed in on these slides. So today, we're going to talk about most of these things. All right, and we already kind of talked about the stator and the rotor already. We're going to talk about the bearings. Here is your anode. We're looking at it from the side. So if we had it like this and we turned it this way, it would look like a big circular disc. Here's your cathode. So here's the filament circuit coming in. Your little filament wire. We have a focusing cup, which isn't even labeled here. Those arrows are the electrons shooting over, and then they're going to hit the anode and make some x-rays, and then the x-rays come down. So that's it, kind of in a nutshell. And then we are going to break all of that down to size. The first side we're going to talk about is the cathode. So we're going to be on the right side. So the main functions of the cathode. These are important. I'm definitely going to be asking you these questions. What are the main functions of the cathode? Well, we need a thermionic cloud. We have to have a high voltage so that we can move those X-ray or the electrons from the cathode to the anode. And we also have to have something that's going to focus those electrons to go to the anode. Because electrons are all negatively charged, right? What happens when we have things with like charges next to each other? Right, they're going to try to repel. So we need something to kind of keep that in check so that they go a little bit straighter across to the anode, okay? So the components of the cathode assembly are the filament. You'll notice there's a little S right there. Most of our diagnostic machines have two. We got a big one and a little one. There are some machines out there that only have one, and that's fine. Those are usually smaller, maybe dental units. But all of our rooms are going to be dual filament machines, and we talk more about that in a minute. The focusing cup, well, that sounds something that would focus electrons. So that's what it does. Focusing cup is this little thing right here. We'll see more pictures of that in a minute. It's going to help keep those electrons traveling as straight as we can without diverging too much. And then the wiring. That's what's gonna give us the high voltage, right? It's gotta be all connected with that big magical circuit. Dominic, is that your absorption face?
Yep.
Okay. I like it. All right, so the filament, we talked a little bit about it yesterday. It's the small coil, but now I'm throwing in like new ugly words like thoriated tungsten. So you do have to know what all of these little parts are made of. I don't know. It's been 5 years of construction outside. Oh, he's just mowing.
Oh, okay.
But he's got his leaf blower on his back and mowing at the same time. He's efficient.
Multitasking.
So,
Sorry, you said that we have to know like what the filament is made of?
uh-huh.
Tungsten.
Thoriated tungsten. Thorium is another metal that is added into that filament to make it stronger and make it more a little bit elastic. So tungsten is the more important one, but thoriated, know that there's a little bit of thorium mixed in there. Does anyone know the word for when two metals are mixed together, or two or more metals are mixed together? It's an alloy. So we're gonna see that word coming up. Anytime you see alloy, you're gonna know that there are two metals being combined.
Nice, spell
Two
that.
or more. A-L-L-O-Y. So we knew that the filament was a small coily wire. Now we know that it's made of thoriated tungsten. And it sits within the focusing cup. So these little doodads right here, these are filaments. You can see kind of that it's a coil. It probably looks hopefully better on your slide. So they are coiled. One is bigger, one is smaller. That's a dual focus tube. That's like what we have here in all three rooms. Okay, so tungsten, we love tungsten. We use a lot of tungsten in X-ray. And it's because it has a high melting point and it is very resistant to vaporization. So that's a new word. Whenever we're loading that little wire up with all of those electrons with the high amperage, it's making it really hot. Well, when things get hot, especially metal, when they get really hot, like 3,000 some odd degrees, they can vaporize. So we want these electrons to come off because we're making X-rays, but then the tungsten actually starts to vaporize. And as that happens in an X-ray tube, you can think of it as like tungsten dust. And so then it kind of comes out and then it settles. Gravity is going to make it settle. Even though it's a vacuum, it'll still settle on the bottom of the tube. We don't really want that. And we talk about why in a minute. It can actually damage the tube and then you have to get a new one. So we don't want things to vaporize. So we use tungsten because it has a high melting point. Its high atomic number is also important. We talk about that in a minute. And it's resistant to vaporization. It still does a little bit, but not as bad as other things. The filament, they're usually 0.1 to 0.2 millimeters in diameter, so they're incredibly small. That's a really blown up picture. The coil is 1 to 2 millimeters wide, and then 7 to 15 millimeters long. Again, there's a range because we have small and large ones in the tubes. All right? And like I mentioned already, most diagnostic machines have two filament wires, and those are called dual focus tubes. You'll hear that used interchangeably. Filament, two filaments is dual focus, and then we start getting into focal spots. You've probably heard that word already. They all kind of are referring to the same thing. All right? There's one larger, one smaller. Usually we call them the large and small focal spot. Depending on what we're going to be imaging, you can choose which one you're going to use. We'll talk about that in a minute, okay? So we can make that decision. That's something we can do whenever we are setting our techniques and stuff. We can decide which focal spot we want to use. Okay? So a lot of the stuff can't change. You can't change your filament size or anything, but you can decide which one you're going to use. Okay? Any questions about the filament?
So you said the large filament is a large focal spot, the small one's a small. Just making sure I'm getting that right.
Yep. So the focusing cup. The top picture is, I believe, from your book. This one's not, but this is another picture of filament. So the little bitty line right in here is the filament. And then these around it, and this whole thing really is the focusing cup. But it goes around both of them. It's got one big structure and then it kind of comes around and creates the ovals around each one. So that's the focusing cup. And you can see on that one, it goes all the way around, but we kind of have it cross section so we can see all the negative charges and the filament wire and stuff. So the focusing cup is typically composed of nickel. Highlight that. It's a metal shroud that surrounds the filament wire to confine the electron beam to a small area on the anode disk. So the anode disk is pretty big compared to the electron stream, right? You can see up there, the little blue lines and the little yellow spot on the anode. We want the X-rays to hit a fairly small area on the electrons, sorry. We want the electrons to hit a fairly small area on the anode. So we want the focusing cup to do its job and confine that electron stream. So another way it helps is that the focusing cup is supplied with a low negative charge. So if that's negatively charged, what are the electrons going to do? They're going to try to get away from it, which is fine. Okay, that's kind of what we want because it's adding to that travel that the electrons are trying to go to the anode. So we're going to apply a really high voltage to those electrons to send them across, but that higher, I know it sounds weird, but a higher negative charge than the electrons have, you know, the focusing cup is more negatively charged than the electrons are, so it's going to help push them along and keep them together. So as the electrons exit the filament and form the electron cloud, the negative charges can begin to oppose the emission of more electrons. So if we have all of these electrons sitting there, but we have not applied the voltage yet, we have this large group of electrons, it's going to make it to where more electrons aren't going to want to be coming off of the filament, right? Because we have all of this negative charge sitting there. So there's going to be this resistance to more electrons coming off. So we don't want to delay it any longer than we have to. That whole thing is called the space charge effect. It sounds like I made it up, but I didn't. So, as those electrons are emitted, a cloud is formed. The cloud contains many negative charges, and it begins to oppose the emission of more electrons from the filament because there's a large negative charge. So this one's not from your book, but you get the gist. We're trying to have more electrons coming off, but there's all of these negative ones already sitting here. So it's going to resist the urge for more of them to come off. So what this does though, how this actually affects us, is that it limits the tube's maximum MA range. There's only so many electrons we can have sitting there before no more are going to come off. Okay? So our MA is our amperage, right? That's the number of electrons that are sitting there. So if we have 100 MA, we're going to have fewer electrons than we would if we were applying 1,000 MA, right? Okay, so it's not as much of an issue when the MA is lowered. And what MA we're using is directly dependent on what exam we're doing, right? We don't need as many electrons or X-rays when we're doing a finger or when we're doing a T-spine or a shoulder, right? Bigger body part, you need more X-rays. So does that make sense? There is a limitation there. And so it limits us to about 1,000 to 1,200 MA. And I think actually the DR room I think is 1,200. That's the maximum we can do. Any questions about that? Like for real?
Did you say that the MA was electrons?
Yes, because it's amperage. And so what your MA is set at is going to determine how many electrons are flooding the filament and how hot that filament is going to be, right? Because thermionic emission required heat. So if we flood the filament wire with 1,000 MA, it's going to get really hot, and there's going to be a boatload of electrons ready to turn into X-rays as soon as the kV then is applied and sends them across.
Do we ever use that much MA?
Sometimes. When we get into like next semester, the higher the MA you're using, the shorter your exposure time. And sometimes like for wiggly kids or really fine detail, you want it to be a really short exposure time. And it's not, I mean, it's not damaging the tube. That's just about as far as we can get because of the whole space charge phenomenon. Okay? Any questions? Because I know this, I understand this is hard, so if I need to say it again, or if it's one of those, I totally get it. Okay, so that's the last slide for the cathode. Is there anything about the cathode you want me to say again, or say a different way?
I know, I'm the same way. I'm just like, maybe if I just go back through after.
Well,
Yeah, I don't know what questions to ask.
well, I mean, that's fine.
Can you maybe say it in a different way?
Which part? The whole thing?
Not so sciencey, no.
Yeah.
Well, we're to the point now where the sciencey jargon, I mean, you gotta slow it down and break it down a little bit though, you know, because it is sciencey, but sometimes there's not a simpler way to say that kind of stuff, like,
Yeah.
yeah, but you can break it down a little bit and go piece by piece.
It's just.
So for exams, to cut out the fluff of the book, would you recommend that we just use the slides and then the review sheet that you give us, or?
For this test, yeah,
Okay.
I would recommend that. Yeah.
So for the space charge effect, what is it basically like? The space charge is the reason why we have to like use a max of 1200.
Essentially, yeah.
Okay. Is
Yeah.
that really like all there is to it? Or
Pretty
is it
much.
like-
And know what the space charge is.
Yeah.
Like, all these electrons are sitting here, they're all negatively charged. The ones coming off are negatively charged. Like charges repel, so it keeps the ones that are still on the filament staying back there. They have nowhere to go because those like charges are repelling. The focusing cup is also negatively charged, and it's trying to keep everybody there so that when we apply the KV, then everybody can go across to the anode. So, it's complicated, but it's simple. That doesn't make any sense, but you know what I mean. Okay, so keep on trucking to the anode. So the anode assembly is the positive side of the X-ray tube. It has three main functions. It serves as a target surface for high voltage electrons that are coming over from the filament. Okay? It's also going to conduct the high voltage from the cathode back into the X-ray circuitry. So it's making X-rays, but we also have high voltage coming across, right? Because those electrons were coming across. So whatever doesn't get turned into an X-ray then needs to be traveling back through the circuitry. Okay? So it's got to be connected that way, and it's also serving as the primary thermal conductor. So we blasted the filament, made it really hot to boil off all these electrons. There is an insane amount of heat generated in an X-ray tube. If any of you are at clinicals and you have a really busy day, or you have a skeletal survey and you did your 20 some odd pictures, wham bam, thank you ma'am, real fast, you can actually touch the housing and it's hot. I have had a patient, or no, not a patient, not my patient, someone else was doing a view you guys haven't learned yet, and they had the patient rest the top of their foot on the side of the tube, and it was hot because we were real busy that day, and the patient was mad. They didn't actually get burnt, it wasn't enough to like singe the skin or anything, but it was uncomfortable for the patient. So there was a lot of heat generated in there, and a lot of that goes out through the anode, okay? So those are the three big functions for the anode. The three components are the anode, the rotor, and the stator. So you've got the disc, and then you've got the turny parts. Oh my gosh, this again. This one's simpler. Simpler? More simple? Because this is just the anode side. So we have the focal track target. Again, there's going to be like 3 more names for that here in a minute. You've got the rotor right here. You've got the stator. You've got some bearings. And then there's your high voltage circuit. So whatever doesn't get turned into an X-ray or released as heat, will then just keep traveling along this circuitry and go back in and become X-rays again. Okay? There are two main types of anodes. We have a rotating variety and a stationary variety. They do exactly what you would think. One rotates, one doesn't. So the top picture is real life. Well, that's what they look like. The stationary ones are a lot smaller. Rotating ones require more components, right? We have to have a whole induction motor in there. So that's why it's bigger. So here's the cartoon version though, to kind of show you the big differences. The rotating ones, they can withstand a much higher tube current because they're rotating. We're dissipating heat better. There's more surface area. All of that I'm gonna say again, so don't stress out about that. The rotating ones are the ones that we use in most general purpose rooms. So all three of our rooms have rotating anodes. Every room you go to at clinicals has rotating anodes. Stationary ones nowadays are used mostly in dental units because you're not having such high radiation doses or intensities when you're doing dental work, right? The technique is a lot lower when you're just trying to get the molars compared to like my sacrum or something. So the stationary ones cannot support a high tube current, so we're not going to be using really any of those. Back in the day, they had some portable units that were stationary anodes, but I think they've gotten all away from that altogether. We're doing more mobile work, we need a higher tube current with those machines. So the materials for these types of anodes, the stationary ones are rhenium alloyed tungsten. So there's that word I gave you a heads up about. So that's rhenium mixed with tungsten. And it's embedded in a copper rod. Copper is a good conductor, right? So that would serve the purpose of sending the energy or the voltage back into the circuitry that wasn't used to be making an X-ray at that time. The rotating anodes are made of all different kinds of stuff. And I've so seen these questions on registry stuff. So that's why I'm going to be asking you all of these. So the disc part of the anode is mostly made of molybdenum. How do you want to say it? Molybdenum. That's how you spell it. That's how I remember how to spell it. I will always say molybdenum in my head. But it's molybdenum, all right? The focal track, or the anode target, that is where we have some rhenium alloyed tungsten, and we talk about the Ys here in just a minute. And then the disc backing, so the back of the disc, you can see on this picture. So there's your focal track, right? And some anodes have two. We'll talk about that in a minute. So there is our rhenium alloyed tungsten, and then the big meaty part, the disc, is the molybdenum, and then the back of it is the graphite. Graphite is light. That's why we want that in the tube, or in the anode, because we don't want it to be extremely heavy. Graphite is light. I'm getting ahead of myself, because the next slide is telling us why we use all of these things. So these are all things we still need to know too. This is all on that worksheet included. So tungsten, we talked about some of this already. We talked about the high melting point. That's why we wanted to use it in the filament. So for the anode, we need a high atomic number. The atomic number of tungsten is 74. I'm not going to quiz you on that, but you'll probably remember because we talk about it so much. We need a high atomic number for X-ray production. So that's a whole other chapter, but that's why. The high melting point, because it's super freaking hot in X-ray tubes. We talked about that already. And it needed to have heat conducting ability. We have to dissipate that heat. We can't keep it all in the X-ray tube or stuff will start melting, like the reels, okay? So, we have to be able to dissipate some of that heat out of there, and tungsten's good at that. Now the rhenium. Why do we have this rhenium tungsten alloy? Well, it adds elasticity. So when things are constantly heating and cooling, they're changing in size, right? So tungsten's not very elastic. If it's heating and cooling and expanding and contracting all the time with tube usage, it'll eventually crack. So they figured out that if they added some rhenium in there, it doesn't really take away from X-ray production, because we still have a lot of tungsten in there, and that's what we need. But the rhenium aids in the elasticity, so your tube life is longer. Graphite, I kind of already said that. It adds heat loading capability, right? We have all this heat, we have to manage it. So we added graphite, and that's cool, because it helps with that, but it's also not very heavy. We need the anode to still be able to spin well, right? Because we use the rotating anodes. So if something's really heavy, it's gonna take more effort for it to spin really fast.
I have a question. Is there graphite on the stationary ones too, or no?
Not usually. And then molybdenum has a high melting point, and it emits a more uniform range of lower energy photons. Ugh, what? Gross. It's getting complicated, but it's good for mammography, basically. That's what's gonna be in most mammography tubes, because if we have lower energy photons, it's gonna be better for soft tissue imaging. Well, breasts are soft tissue, so we don't need the tungsten atomic number to be producing these x-rays. So molybdenum is added in, it's got a high melting point, it adds strength, it's great. In our tubes, we still have tungsten for the main target area for producing x-rays, but molybdenum is definitely more of a mammography tube thing. I've also seen that on registry stuff. Okay? Everyone looks miserable.
Yeah. Got it.
I need more classes.
What?
I mean, I like this, but I don't.
Oh, Lisa, don't start.
All right. Target area. This is a real up-close picture of the anode. So this is the part where it's like facing the cathode, right? So now we're looking at the actual disc, not really the profile side of it. So the target area is where the high voltage electron stream is actually going to be making impact. It's also called the target, the focal point, focal spot, focal tract, blah, blah, blah. It's got all kinds of names, which is unfortunate because focal spot, we talked about focal spot with the filament, but it's related to all of this. So we'll tie it all together here in a minute. Focal tract, focal point, target, all of that. I'm honestly going to be calling it the target, because that's where the electrons are actually hitting. So you can definitely tell where that's happening. So as these electrons are constantly hitting it, and the anode is being bombarded, it can actually become pitted after a while because of this constant bombardment of electrons. It's the area of X-ray production, because that's where the electrons are hitting. This is considered a point source of X-ray photons. We'll talk about this later. And this is where your SID is measured from. Has anybody noticed that it doesn't start at 0? When you're measuring your SID, like when you pull it down, it's usually 10, sometimes 12, just depends on the manufacturer, because you're actually measuring from that point source of the target, not just the bottom of the collimator light, or where the tape measure is coming out. So that's why you're going from the source, because SID is, yes, exactly. So the source is the actual spot on the anode. Stationary anodes have a static target area, because it's not moving, right? It's stationary. Static means not moving. Rotating anodes have a dynamic target area, which helps us in several ways. We have a bigger surface area for the electrons to hit. Surface area is important for X-ray production reasons, but also for heat reasons. If we had that big disc and we were just blasting that same spot constantly with this high voltage, it's going to crack it. it would not be able to sustain that. So by it rotating, it lengthened your anode life, which lengthens your tube life, but that surface area also is better for X-ray production. The rotation helps with heat dissipation and surface area, okay? All good fun things, right? So, the target area. This picture is in your book, so it's gonna be probably better for you to look at it there, because that looks blurry. Page 85. So, this picture right here is just that bottom of the anode. So that whole disc is way up above there. We're just looking at this bottom chunk where the target actually is, all right? So we're gonna use these terms a whole lot moving forward. The actual focal spot is the area of the focal track or target that is actually hit by the electron beam. So, right here, boom. Actual focal spot. That's where the electrons are hitting. Now, the effective focal spot is describing the area of the focal spot that is projected down to the patient. So you can see here that this is coming this way. That's the actual focal spot where the electrons are actually hitting the target. That's how I always remember that. They are actually hitting it. Then this one coming down is your effective focal spot. That's the one that is projected down to the patient. Or the object, whatever. Okay? So you can see the only difference, well, the starting difference, I guess, is the size of the actual focal spot. So this is small actual focal spot. So we are using the small filament in the cathode. Okay? So they selected the small focal spot or small filament, same thing. And so we have a small actual focal spot hitting the target. When that's small,
In what scenario would you use this?
we get there. So when this is small, the effective focal spot will be small too. Then, if you directly compare it, when you have changed it to the large actual focal spot, meaning you picked the large filament on the cathode side, the actual focal spot is now bigger, and now your effective focal spot is now bigger. So the area coming down to the patient is bigger. This is before collimation, before all of that stuff, okay? How's that at this moment?
Sarah, you said that actual, that's not what I thought. It'll come back.
Roger that. Okay.
It will.
I know. Do you need a potty break?
Yeah.
Or just like a mental, get away from Sarah? That's fine. 10:40. Be back at 10:40. We're about halfway through, so we gotta wrap it up.
You know what, Sarah? Going through things. You need to stop. Like, I'm trying to focus and you just crack me up all the time. No, so going through these slides, the first time I sat through a observation class for like before I was in the program, and I was virtual, but I'm pretty sure it was this lesson, probably, because like all this stuff, like, but I remember because I was in chemistry at the time. I know how to, but it was like it made sense, like the way you're talking about it, and yeah. And now that like we're going through this again, I'm like having flashbacks of like things I was writing down to put on my little piece of paper. Go ahead, Nicole.
No, I
Before you
appreciate
lose
it.
it.
Thanks.
So sorry,
electrons are.
No, you said how do you actually?
Yeah, how I remember, so the electrons are actually hitting the
Okay.
electrons are actually hitting
So okay, so actually hitting.
See, the science parts of these classes make sense to me, but in my real life, like all personal stuff, nothing makes sense to me. I think that's why I like science. Something makes sense for once.
I know.
So I mean, basically, what you were getting at there on the actual focal spot and effective focal spot, large filament equals large actual slash effective focal spot, small filament equals small actual slash effective focal spot.
Yes. And then the next slide makes it worse.
Yes.
Mario, she's
Preparing you.
I looked over at her, the way she was just so different. Caffeine is my drug of choice. What am I doing?
I appreciate the warning at least.
I know. I just know my burning
Molybdenum. Is that right? Molybdenum? Molybdenum. Molybdenum.
15 now.
No. When you go to a car, because that was what No, I parked right where the building is. Oh. The Dodge building, I parked literally right there. Yeah, no, they're really nice. Oh, it made it?
Equals actual focal spot.
I'm more worried about walking thing and if it's like raining or snowing and I have to like walk outside that dog. Like it's like a 7-minute walk. And that doesn't include rail at my sandwich. You have to wait for cars. They do give you a little rest. Yeah, I was good. And then I don't, cause like if you park in the south, like my sister's like this walk that is so
Have you done any of the boot camps yet? I thought it was odd that they chose to do, like, they have the questions in like the order, you know, like they had for the first boot camp. That you used Oklahoma like some of the first two, and then they did Oklahoma in the last two. I wouldn't have been more helpful to do the law first. Oh, look, I like my your notebook is. That is awesome. I love it.
Okay, making our own. It's 12:40.
Oh, what's it called when you, no, something that's like, made just for you. Oh, why am I blanking?
I know what gravel you're talking about, but I don't know what the process is. So I would walk to first time to go to the main entrance, like wherever you know how to get to the building. So like when you got here the other time, you parked right in that little garage, like right outside the main entrance. Right, right. But then you realize, what? Right out. Okay. So, it's Taylor, like walk down the street,
Taylor,
get in there that day and then ask like where you cut
Personalized.
this.
There was the word, I was like, oh my God.
They're gonna
Yeah,
do
yeah,
it.
customized.
Like if on that bus, just most of them is mine.
You would?
I'm just curious again.
No, I would the first day, allow yourself the time to go in the main door and then ask them, because they're gonna know. Because when I go, I just park in the visitor parking up at the top.
Okay. Oh, are you talking about Truman? Yeah, we have to park in like the Scrabble parking lot that's far away. Yeah. Let me tell you something though.
We gotta go.
City.
You guys can talk after class. We gotta move. We're only halfway through. Okay, so we just talked about actual and effective focal spot, right? So we can manipulate these things by adjusting the angle of the anode. So that last picture, had both of them at 12 degrees, okay? So this is the angle right here, right? Does that make sense? Because sometimes that's like a hard one to picture. So this 12-degree angle is this right here, okay? From 90 degrees. We are going 12 degrees over, all right? So some anodes have larger, maybe smaller angles than that. So if we increase our anode angle, that's going to change the size of our effective focal spot because of that angle, because that's the one coming down, right? So you can see in these two pictures, that electron beam or the actual focal spot is the same, right? Because that's determined by the focal spot or filament that you're using. So the actual focal spot did not change. The only thing that changed is the angle of the anode down here.
Okay, so you said increased anode angle changes focal spot? Focal spot, okay.
Effective focal spot.
Oh, okay.
So the actual focal spot is not changing because that is your filament.
Oh, okay.
So you're either picking the large or the small. So right now we're using the same one. We'll call it large. The only difference is this anode angle is 12 and that one's 24. So if you look at how that hits and then what is projected down, so that's a little bitty angle, we end up with a small effective focal spot. If we have a larger angle, now this area is bigger, right? And it's because of that angle. So when we increase the anode angle, we have a larger effective focal spot. This is called the line focus principle.
That's the
It's
most
gotta have a name. Huh?
That's the most that you've made today. Just saying.
Thanks.
You're welcome. At least for me. Just saying.
Yeah. All right. Well, good. I'm not gonna keep talking about it then. We're gonna go.
You go.
Get her rolling. This is just kind of more stuff, but that's what I've already said. It's just saying it a different way. This though, this is important. Anode angles range between 7 and 17 degrees. Most common is 12. Remember those numbers.
How was the other one, 24 then?
It's just an example.
Oh.
Man. Just roll with it.
Okay.
We're doubling things. We're talking about bigger stuff. Just go. I don't write the book. Don't want to ever. God, kill me if I ever say I'm writing a book. So, the kicker though with smaller focal spots is that it can mess with the size of our primary beam at shorter SIDs. So now you're going to be mad because now this is sometimes more difficult. So, when you look at this though, so we have larger, smaller, effective focal spot. We got that. Well, now we're kind of translating this into our primary beam, like what's actually coming down to the patients. So when we have this smaller angle, we have a little bit of a narrower, useful beam. When we have the bigger angle, we have a wider, useful beam. Well, you remember when you were doing your AP chests supine on the table in the CR room, what were you having to do? Yeah, you couldn't be detented. You had to lower the table all the way down. You had to smash the tube all the way up to the ceiling, right? Because you needed a longer SID. And that's partly because of this same thing. You can't get the whole body part on there if you have a narrower primary beam. And that happens at shorter SIDs. So sometimes that will be a thing, all right? So just remember, smaller focal spots can hinder the size of the primary beam at shorter SIDs, okay? Anyway, I already said this too. Dual focus tubes have a small and large focal spot. These small ones, so this is what Kendall asked earlier. When are we gonna use these? When do we decide? The small focal spot is gonna be better to use if you're looking at fine detail.
God bless you.
So if you think about it, what would be something we're looking at fine detail? Fingers, elbows, wrists. How about a pelvis? Not really. A pelvis is also going to require more photons because it's a bigger part, right? So it would make sense that you're going to use the larger focal spot for a body part that's going to require more photons. So it is detail. You do get better detail with the small focal spot, which is fabulous, but you also don't need as many x-rays, so you can use the small filament to do the exam. Now, 99.9% of the time, this is all automated in the machine. Like, they have protocols built. They know if you select a finger, it's going to automatically choose the small focal spot. If you're doing a pelvis, it's going to automatically have it set up to do a large focal spot. All right? So, but that's why it's also important to pick your exam. Don't be shooting a finger under a pelvis. Smack you if I see you do that. I won't, because I would get in trouble, but I would want to. Make sense? Yes, okay. All right. I also like to call this the anode hell effect because this, for some freaking reason, when I was in school, was really hard for me to get, and I don't know why. It made me very angry, but I got it now. So, the little picture at the top. It's in your book. Don't know what page. 87. Okay. So, we got a lot of red dots, and we got little squiggles. What did I tell you like the first couple of weeks? The squiggle's always going to be in your pictures. Some type of energy x-ray, right? Sometimes gamma look like that too. But, so those are x-rays. So those electrons have hit the anode, and they've become x-rays, but now they're like, where the hell are we going? Some of them are going where we want them to. Some of them are going back up in the anode, like C's shooting up. D's going back to the cathode. Nah, we don't want that. But we have to deal with it. Ideally, we would want them all to just come straight down, right? And become our effective focal spot, and be our primary beam, and go to the patient. Well, that doesn't always happen. So this bottom part of the anode, this right here, that's the heel of the anode. So what happens when these x-rays are going all wonky directions, some of them get absorbed in the heel of the anode as they're coming down. Some of them are, I mean, you know, like C and D, we'll talk about those later. There's a word for those too. But A, that is getting absorbed by the anode. Or it's going to maybe create another x-ray that has a lower energy. Something like that. But what that does to our beam that's coming down to our patient, so that was an x-ray photon. We wanted it to become part of our beam, right? But now it's not. So because of this random absorption in the heel, we end up with a beam that has less energy on this side of the beam. So the x-rays come down, and they come down as a pyramid, right? They disperse. So this side, because of that extra absorption there, always has a little bit less energy than the cathode side of your beam. I mean, these two bullets are kind of just what I've already said in the shortened version, okay? So, that's why now there are numbers to remember, because it varies the useful beam from one end to the other by up to 45%. That's a big difference, right? If we're shooting a big body part, there are times when you can actually tell. It's on the next slide. And you can use this to your benefit as a technologist too, because the anode heel effect doesn't really go away. something we gotta deal with. So there are about 20% more this part, I'm not gonna ask you these numbers, this is just for your information. 45%, that I'm gonna ask you. But there's about 20% more photons, photos, look at me sucking with that. Photons at the cathode end, and about 25% fewer at the anode end, okay? So, but that's where that's where the 45% comes from. Now, that angle of the anode makes a difference. So if the anode angle is smaller, you're gonna have a larger heel effect. So I'm gonna go backwards just a moment. So looky here. Do you kind of see why? So we said a smaller angle is gonna have a more pronounced heel effect. Your your effective focal spot has more, like there's less divergence, right? Because of that smaller angle. Now more of them are gonna get absorbed over here because there's just less area for them to go. So if we increase this angle, man, we have a much wider angle, useful beam, less of them are gonna be getting absorbed over there. So the heel effect is more pronounced where there's a smaller anode angle. Cool? Okay. So how can we use this in the real world? Well, we're going to be imaging things with greatly differing thickness or mass density. Mass density always bothers people. Just think of it as thickness. So my femur, and I'm not shy, I got a big old butt. So my upper femur is thicker than my lower femur, right? So on someone of my size, you could probably use this to your benefit. So how would you lay me on the table?
Your legs will be over here, and then your booty will be up here.
Right, you want the thicker part of that structure under the cathode side. Right? Fat cathode. Remember that, write it down. Tattoo it on your face.
Can you see that all over again? Sorry.
Yes. So, when we are imaging structures of varying densities, right? Like my femur, the T-spine is another one. So when you're into the upper T-spine, we have a lot of lungage, right? We don't need a lot of x-rays because it's just the bone and maybe some shoulders. The lower T-spine though, you've got belly, you've got breasts, you've got congestive heart failure, all the things in the way. So you would want to use it to your advantage. You would want the higher side of intensity for your beam, which is the cathode side, to be over the thicker part. The thicker part of that part. I don't think I'm helping you. I said to say it again and then I complicated it. But you want the thicker part of the body to be under the cathode side because there is a higher intensity of your beam there. Huh?
Can you show like where the cathode side is on that? Like where?
So the cathode's always on the right.
So you like when you're looking at it, it's on the right.
Yep. So for a T-spine, for my femur, I'd be like this, right? And the anode is over my head, and the cathode is over here. So if I'm gonna do a T-spine on me or a femur, position me like this, so that the thicker part is over.
I was like, let me get up there.
For my femur. So for my femur, my butt would need to be on the cathode side. For my T-spine, because I need less intensity here, I would have that on the anode side and have the lower part of me, the lower part of my T-spine on the cathode side.
So varying density, thicker part of the body under the cathode side.
Fat cat.
Yeah, fat cat. That makes sense.
I guess I should make this bottom one say usually marked on the machines. That one's okay. Oh. Alright, we talked about a couple of these already. This last part should go a little faster than the first part. because we already know how an induction motor works, right? So, this is not from this book. This is from the old book I used to use, but I really liked it because you could see a good cross-section picture of the rotor and the stator. And you can see how those windings, each one is gonna fire, and then the rotor will try to align itself with that magnetic field, but it can't because the magnetic field's constantly changing, so that's what makes it spin. One thing that's kind of new though, the stator is located outside of the vacuum. So whenever I showed you those pictures of the X-ray tubes, the stator kind of goes on the outside of that, outside of the glass part. Because the mechanics of the stator would not be able to withstand that amount of heat and the voltage that are there inside that vacuum, okay? Now, if an induction motor fails, your rotor's not gonna spin. Well, that sucks. If your rotor's not spinning and you try to expose, you're probably gonna crack your anode because it's gonna get too hot in that one spot. Remember, we wanted it to rotate because it was gonna share the wealth. That thermal dissipation of the heat is something that we need. So, and if it's not a high enough exposure or hot enough, it could at least melt a pit in it. And that also sucks. That also means that you need a new anode. So that can happen from just one exposure. If it's not moving and it's hot enough, or a high enough exposure, it can cause that. And if you don't get a new anode, that's gonna really mess with your X-ray production. So when those electrons for a future exposure would hit that area, can you imagine what it would look like on that last picture, that top one? They'd be going even wonkier places. So you don't want them to be worse than that. With that we can manage, okay? But if you're trying to expose and your anode's all pitted and nasty with big spots like that, your X-ray production is gonna become very inefficient.
I have a question.
Yeah.
So, I mean, because most of them are like, all these like, the components inside the tube are like controlled by the computer now. How do you know when your anode is?
We'll get there.
Okay.
We're close. So, a little bit more about the rotor. This is inside the stator. This is also inside the vacuum of the tube. The rotor is comprised of a hollow copper cylinder. I mentioned copper before with the stationary anode, right? We still have copper because we still need to be conducting that extra voltage out of the tube. So whatever doesn't get made into an X-ray on the anode then kind of travels down the shaft through that cylinder, and then that's what's connected to the rest of the circuitry. That cylinder is attached to the anode with a molybdenum shaft. So here's another fun fact for molybdenum. It's a poor heat conductor. Why would we want something that is a poor conductor when I've been rambling on about heat dissipation all day?
We're trying to send the X-rays out of the tube and it would pull the electrons more towards it?
Sort of. What were you gonna say?
Oh, I was just gonna say that it would burn up, it'd be too hot in there.
Right.
So you wanna
It's
pour
a
it
moving
out.
piece, you want it to be as cool as possible, as quickly as possible, so the less heat you can conduct, the better.
True. We also have these ball bearings. And if those got really hot, then they're gonna warp. I'm kind of getting ahead, I think this is on the next slide. But if we warp the ball bearings, because that shaft is right in the middle of all those ball bearings, we have to have the ball bearings to allow for the spinach. Spinach? But if we have, I'm sorry, God, this is not helping. So, if we warp the ball bearings though, that's gonna affect the way it's spinning. And that would lead to a wobbling anode, which is not good anyway, because if it wobbles, that's gonna cause some other mechanical malfunctions. But if it's a wobbling anode and your target is wobbling when the electrons are coming across, that's also gonna impact your X-ray production in a very unfortunate way. All right? So, the cylinder is what's affected by the electromagnetic field of the stator, causing it to rotate. That's what that bottom picture is all about, and we've already talked about it. So, moving on. Common rotating anodes operate at about 32 to 3600 RPM. Highlight that. High-speed anodes are going to operate more around the 10 to 12,000. When we talk about high-speed anodes, that's more like for angiography, IR, cath lab type stuff where they're taking.
No, I'm just being, I like that.
Do it. Now you do. Yeah, highlight it.
Yeah.
Do it. But the higher speed anodes are for areas where you're taking a ton of exposures very quickly with high technical factors. So like cath lab, you know, when they're blasting all that contrast and looking at your heart and all your vessels, you're taking a lot of exposures really quickly, and they have to have an anode that can withstand that. So it's a little different than our room.
And you said that would be the second one, right?
Yes.
Would be cath lab.
Right.
The 10,000.
So, when we're at clinicals, please tell me you actually like pulled the trigger last week.
Yes.
Did it feel
It's not a
good?
trigger though, it's a button.
Stop it.
Yeah.
It's like mine's literally just like a flat button and you just go.
Yeah, I don't like the buttons. I need it to be in my hand. Okay, so, but you push it halfway, what happens?
Start. You're welcome.
Right, so you push it halfway down, your rotor starts rotoring, right? It's rotating. There's one other thing that's starting to happen when you do that. And we talked about it, well, yesterday and today. What are they doing? Yes. So that filament is getting flooded. I knew what you were saying. Getting flooded, right? So we have thermionic emission happening at that moment. So when you push it halfway down, the rotor starts spinning because it takes a second for it to get up to 32, 3600 RPMs. So it has to get up to speed. That filament has to get hot enough for thermionic emission to happen. And then finally, when you push it all the way down, what's that last thing that happens?
Shoot.
They do. What makes them shoot?
Voltage.
Shoot. Yes, the high voltage. Thank you. Yes, so you push it all the way down, then your KVP is like, woo, let's go. And it like pushes all those electrons into the anode, X-ray production happens, and boom. But that's also why it's not immediate. If you just jam it all the way down, it takes a second, right? You don't immediately hear the boop. It's got to spin, the filament's got to get hotter, and then it'll do it, all right? So that's what's happening when you push the button, okay? Isn't that nice? Now you know, like, what's
We just
actually...
like to know that we push the button and then we make a pretty
Then the
picture.
big
Yeah.
Yeah, I understand. Okay, now, if you are one of those rotor happy people, and you just like to hear the noise, that's probably not cool, because it's gonna wear out your induction motor, and it's also gonna wear out your filament. And if you bust a filament, it's just like in a light bulb. Literally the same thing happens. Maybe not today's light bulbs, but the old ones that had the tungsten wire in them. Boom, same thing happens. Then you gotta get a new tube. I think the book said a tube is roughly 10,000.
Yeah.
But then you have labor, because they gotta take the whole thing apart and put in the new one. So, if you are finishing this program and you're like, I'm gonna go into biomed and learn how to fix this stuff, I don't blame you, because it's a good job. You don't have to lift up heavy people. Okay, now, I talked about ball bearings already. They're silver plated. Silver plated ball bearings. That silver plating acts as a lubricant. We could, most of the time, there's grease, like in your car, or some oil lubricating ball bearings. We can't really do that up here because it would get too hot, the oil starts to evaporate and it makes a big mess and it's gross. We don't want that to happen in the tube. So we silver plate the ball bearings to kind of eliminate that. After an exposure, the rotor should coast for about 60 seconds before stopping. Have you heard that already? Maybe, and like at Children's, whenever we would do a skeletal survey, it was 26 pictures and we could get that stuff done in like 3 minutes. Boom, 2 of us. We ain't handling that kid everywhere. But the person shooting was like, doof, doof. So the rotor would never stop spinning. It would spin for those whole minutes because we were shooting them so fast and it didn't have time to stop. So they do accommodate your workflow in a way, but we also went through tubes like every 4 years in that room, if not quicker than that. So they should coast to a stop. If you start noticing that it's less than 20 seconds, and now I've never stood there and counted, honestly. But if it doesn't take very long for it to stop coasting, that's a good sign that your ball bearings are getting warped, because it should take longer than that. Means the ball bearings aren't working. If high temperatures are used for too long, the heat in the shaft can melt the bearings, and that's unfortunate. So that's partially why we use the molybdenum in the shaft, because we don't want the heat to go into the ball bearings, because it can warp them, and then you have a wonky rotation. Tube failures in the anode assembly. And this is kind of just a review. So we can have severe anode pitting. That can lead to tungsten vaporization, which we talked about. If that settles on the glass envelope, that can affect the tube. It can plate the areas of the glass envelope and the window of the tube. So there's the whole glass envelope. That area where the x-rays are actually coming out is called the window. It's a little bit thinner. That way it doesn't take away from our x-ray beam. Since tungsten has that high atomic number, it can actually attract the voltage that's coming out of the cathode, and it can arc down. And if that voltage arcs down and hits the glass, it cracks the glass. So that's how you can mess up the vacuum. And if you mess up the vacuum in the tube, then you have no tube. You gotta get a new one. If anode temperature increases too much, it can crack the anode, which I've talked about already. It unbalances it, and then it doesn't rotate effectively. Maximum radiographic techniques should never be used on a cold anode. Did anyone warm up a tube at clinicals last week? Okay. If you're at a small hospital and you're there first thing in the morning, chances are it's going to tell you that it needs to be warmed up. If you're at like North Kansas City where the rooms don't stop ever, probably ain't ever going to have to warm that one up. But it's something, there's like a warm-up process for each room, and it's different for any manufacturer, but it's a series of exposures of different lengths and different intensities just to get things literally warmed up so that you don't crack an anode. If you're going to do a pelvis or a lateral lumbar spine on like a 500-pound person, you don't want to do that on a cold anode, ever, because that would be bad. If exposure times are prolonged, the anode and shaft can heat up too much to cause, then we get overheated ball bearings, and then we don't rotate. Okay, talked about all that. Now, briefly on the envelope, we have 5 minutes, guys. Can we do it?
Yeah.
All right, good. I want to get through this so we can review. So, cathode and anode assemblies are enclosed within a glass or metal envelope. Already talked about that. If it's glass, it's Pyrex glass, just like your pie dish at home. They're about 10 inches long, about 6 inches in diameter. There are now metal envelopes, which is a little helpful now. More and more of them are metal. Back when I was in school, there was no metal envelopes, but it does help with that tungsten thing. So if tungsten does vaporize and sit in the bottom of a metal envelope, that arcing that could happen won't break the envelope. It won't break the vacuum. So they are switching more and more to metal envelopes.
Is there a specific metal that they use?
Probably aluminum or something light, because then it's lined with lead. We'll talk about that in a minute. Or not the envelope's not lined with lead, that's the housing, sorry. All envelopes have a window. That was what I said before. It allows for less absorption of x-rays as they exit the envelope. So this would be the window down here. Probably not down here, that's the housing. We're getting all mixed up because I'm trying to hurry now. Okay, now the protective housing. That's the big part that you can see over there. It's going to help control leakage radiation. Don't freak out about leakage radiation. We won't talk about it. It's not like it's just shooting out all the time. It's going to help with scatter radiation, and it helps isolate the high voltage and allow for cooling of the tube because there is oil. So between that protective housing and the actual tube itself, there is oil that is circulated around it, and that helps for that thermal dissipation. We got to get rid of some of that heat. So, like we mentioned before, X-rays produced at the anode are emitted isotropically, meaning like all over the damn place. The primary beam, we want to exit out the window. Everything else, we want it to be absorbed and not escape, right? We don't want to be maybe holding the patient and then have X-rays coming out of the tube at us. So, That housing is lined with lead. Lead is a major absorber of X-rays. We talk a lot about lead later on. And the oil also does help. The oil and all of that helps insulate against shock, like us, you know, there's a high voltage within that tube. If we touch it, we're not getting shocked, so that's good. And provides heat dissipation. Some machines, like the high capacity ones, will have a fan in addition to all of those things for additional cooling. So I mentioned leakage radiation. That is radiation that does escape the protective housing. Lead is not a one and done type of thing. We get really deep into that later on about how effective lead is at absorbing X-rays, and it is very effective. However, there is still a chance that something can escape. So the protective housing must be designed, this is a highlight, it's bold. It has to be designed to reduce leakage radiation to less than 1 millirankin per hour at 1 meter away from the tube. It's a lot of ones, don't mix up your units. 1 millirankin per hour at a distance of 1 meter from the housing. Okay? And I quiz you again on that in like 2 other classes, so. We keep talking about it. So, the other thing we gotta deal with is off-focus radiation. So the projectile electrons should only interact with the target of the anode, because that's where they're headed, right? We do all of these things, the focusing cup, all of that to make sure they're hitting the target of the anode. But what happens after that can get a little crazy. So after they hit the anode the first time, they can bounce off the target and hit another area of the anode. And then they make another X-ray. And then that one is usually called off-focus or extrafocal. There's 2 words for that. All right, so that's what this picture up here is kind of showing you. You've got rebound, you've got the electron beam coming in, you have extrafocal X-rays, you've got how they can rebound and bounce back up to the anode and make another X-ray. So, if they do that a few times and then make it down through the window in the envelope, they can come to your patient. Well, that's increasing their dose. The low energy X-rays don't really help our picture much. And then actually, if you have your collimate, you know, your collimator is open, but this is a DR or CR image, so we were able to take off the masking. That's why you can see the shadow of the nose and the chin on the outside. It's those extrafocal X-rays that are doing that. They weren't high enough energy to be a part of our primary beam because they bounced around too much up in the anode. Okay? So that's what the extrafocal or off-focus radiation can do to us. Is everyone actually okay with keeping going? Or do people need to leave? I'm like, be honest, because we can stop and we can finish this Tuesday, or I can just keep going.
Got 5 slides.
All right. So, you guys were looking at those graphs and thinking, gross, they are honestly not that bad. As long as you can look at the labels and read a few numbers, it's gonna be fine. These are rating charts, and they tell us a few different things, but all of it is to help avoid heat damage to the components. Now, the manufacturers make these rating charts. They used to be posted up in the rooms. Now, most of the time, they're just stored on the hard drive within the system, and you can pull them up if you're super curious. But this is what the physicists do. This is what the people that are installing the rooms, this is stuff that they're concerned about. As a technologist, you can be concerned about it if you want. Never have I met someone that was, but that's okay. There are 3 types. There's a radiographic tube rating chart. That's the one that's most valuable. What it's telling us is maximum technical factor combinations that we can use without overheating the tube. So technical factor combinations are KVP and mass, right? Those are the big ones. That's how we're generating all of this heat, right? Amperage and voltage. The other kind is an anode cooling chart. This is telling us how much time we need to let it cool down before we start damaging something by doing additional exposures. So we got one of those for the anode, and then we got the same exact thing for the actual housing around everything. They look almost identical. And they're telling you the same thing. How much time is needed for the housing to cool down before we can take another exposure and not damage something? Okay? So we're gonna briefly talk about each one. So this is a tube rating chart. It looks yucky, but when you look at each piece, it's not so bad. So the curve, the red lines, those are all labeled with different MA levels. Okay? The y-axis, the one going up and down, is your KVP. The one at the bottom is your maximum exposure in seconds. Your MA and your seconds are your max, right? So, for any given MA level, if you combine KV and time, so we are going to pick 0.2 for the exposure time and 60 KVP. So, we meet at this point. Well, this point is below all of those lines. So that KV and seconds combination with any of those MAs is not going to be any damaging. It's not going to be damaging. It's not going to overheat the tube at all. So if I'm feeling crazy and I'm going to do 4 seconds, so right here, and I'm going to do 110. So I go up to here, I meet that. So if I do 110 kV with a 4-second exposure, it don't matter which one of those MA stations I select. We're going to mess some stuff up. Okay? So that is not safe. You would definitely damage something. If the combination is under the curve, then it would be safe. So if I have 1 second and 90, what MA could I possibly use that would not damage something?
175, 200, 150.
Right, either one of those, 125 or 150 MA, because that's underneath those curves. That combination would not be kosher with 200 or 250. It's too high of an MA with too long of an exposure. We're gonna mess stuff up, okay? So it looks gross, but make sure you're reading over that. But that's exactly how I'll ask questions. Is this a safe combination for this MA station? All right, well, that's exactly how I'll ask those questions.
And no notice the chart like that.
Yeah. So, now, an anode cooling chart. Now we're talking thermal energy, which we measure in heat units. Here's the equation for heat units. It's not that bad, because you're going to have all the information right there ready to do it. You're going to take your KVP times your MA times your seconds, and then there's this ugly rectification constant. But there are only 2 of those. And it's going to tell you if it's a single phase or a high frequency generator. So we talked about single phase rectification yesterday, right? This is what we're talking about. We're going to talk about high frequency stuff later on. So there's only one, you're going to pick one of those 2 based on the problem. There's examples on page 92 and 93, and we can talk more about those on Tuesday when we review, but I want you to make sure you look at them. So what you got to do is figure out the heat units, find it over here. That's what's over here. You've got your time in minutes. This is the cooling line, right? So what you're going to look at is the thermal capacity of the anode and how well it's dissipating the heat. So for the chart to the right, it has a 350,000 heat unit maximum. So that red curve goes all the way up, and it goes all the way to 350, which 350,000 because it's times 1,000, okay? If that heat unit amount is reached, so if you have hit that 350,000 heat units, you have, I don't know what you did x-ray, but it would take 15 minutes for the heat units to then reach 0. So there's your heat units. For it to cool all the way down to 0, you look at your time in minutes. And when does it intersect? 15 minutes. Okay? So it seems gross, but that's really it. Yes, and look at those examples on 92 and 93, but again, we'll go over those Tuesday when we review. The housing cooling chart is the exact same thing. Sorry, Nicole. You're like, I'm just gonna go ahead and wet myself.
I just don't want to get sick.
I know.
You know?
But this is exactly the same thing. And kind of silly thing I always thought is, if we get to the point where we're worried about the housing cooling, the anode's probably already toast, because we're gonna burn up the anode before we mess up the housing. But anyway, so we don't use this one a whole lot, but it's the same thing, all right? Cooling time for tube housing is typically 1 to 2 hours after that maximum heat unit is reached. So you would look at it the exact same way.
And it's the same formula as the last slide too.
Yep. Recommendations for extending tube life. This is what you should do, okay? Warm up the tube, helps prevent a cold, cracked anode. Do not hold the rotor down unnecessarily. We already talked about why. Use lower MA levels when you can. Obviously, there are larger body parts where you need high MAs. Don't think you can't do that, okay? But it does wear and tear the filament, and that's something we have to deal with. And then there's a table on page 94 that has these and then some other ones, okay? So, I posted the review worksheet before class. It's got the due date on there. I am gonna do, you want me to do 2 different quizzes? One for each chapter or just one big one? 2 different ones. Okay, there'll be 10 questions. The due date will be next Tuesday night, right before the test.
Is it worth points?
Those will be, yeah.
Okay.
Quizzes,
Yes,
both due by next.
yeah. And they'll be in there. The worksheet